Good afternoon. I'm CCP Loki. How are you doing this afternoon? Anyone hungover or because this time you need to kick your brains into gear. I'm deeply honored and privileged to announce on stage the man who discovered the first planet outside of our solar system. In 1995, he discovered the planet, and since then we have discovered 4,000 exoplanets, and the count is going up. This is a man who can probably claim the title as the father of planetology. Please give a warm welcome from the University of Geneva, Michel Mayor.
Hello, good afternoon, everybody. I'm very glad to open a little bit the window for you to search for extrasolar planets. I will not discuss of the game itself, but try to be a little bit more broader to give what is the context of exoplanet research. No. Oh, it's difficult to search for planets. Yes, this is the question, as the most important question people are working on right now. Okay, for 20 years and a little bit more, we know that a lot of planets exist in the universe, in the galaxy. But the next very big question is, are we able to detect signature of life on some of these exoplanets? So this will be one way to answer the question or the hypothesis done by Christian de Duve, Nobel Prize in Biology, that if you have the good condition for the development of the complex chemistry of life, it supposes that life will emerge automatically. So in such a case, we will have a lot of possibility of sites in the universe where we have life. So this is the most important track of the present research done by many of my colleagues. So probably most of you know that we are part, the solar system is part of the very big system. It's called the galaxy of the Milky Way. This is not our own one because we don't have the possibility to go out to take the picture. So something like 200 billion of stars similar to the sun. And the question is to know if you have some planet orbiting some of these stars. Evidently, you don't have possibility to see every star itself, but you see that you have big blob of clouds, of red clouds of gas. It's molecular clouds. This is a place where is the origin of stars and planets. If you are looking at only a very small piece of the our own Milky Way in the central part, you see that you have as many stars you want. You have billions of stars, and the question is to understand if you have some planet orbiting that star, that one, and so on and so on. This is a question we are facing for many, many years. And most people believe that, okay, it's evident that we should have a lot of planets in the Milky Way. It was not always the case. If you are looking back, the literature of the astronomical literature, these are all very big names of the research in astronomy. This is a logarithmic scale. Here are the years of the last centuries. And you see that here is 0, 100, 10,000, and so on. And you see that until 1943, all astronomers believe we do not have any planetary system in the Milky Way, except our own one. Or maybe people was careful to say, oh, maybe we have few. So you see that people do not believe that we have other planetary systems in the Milky Way. And suddenly, due to different detection, in 43, the paradigm changed, and people suddenly believe, no, we should have planets everywhere. And you see that we are between 1 billion, 100 billion of planetary systems in the Milky Way. So it's a relatively recent change in the mind of astronomers. So looking back to the image we have of the Milky Way before, you see this is very well known is the Orion Nebula. This is the place where you have the formation of stars and planets. "22 years ago, the Hubble Space Telescope did some images of young stars in front of the Orion Nebula. It's a very big cloud. It's something like 100,000 times the mass of the Sun. So it's a really massive cloud of hydrogen and helium. And if you are doing the image of some young stars, you see always you have a small disk of dust and gas orbiting fastly around the young star. So this is the place where you have the formation of new planets. And it's evident the physics is the same everywhere. So if you have the possibility to form planets here, it's the same here, here, or here. So a priori, planetary systems are only byproduct of the formation of the stars themselves. So a priori, we can imagine that you have billion of planets in the Milky Way, or maybe more than stars, because as you know that in the solar system you have several planets. So today we have several techniques to detect planets. The first one was my own preferred one, is the Doppler spectroscopy. I will say a few words on this. And then after, it's a technique used to detect planets by the transit. And this will be the core of the activity to be carried out in the game you are for what you are here. And you have other, and the 4,000 planets detected today are mostly coming from these two techniques. And I will not describe the other possibility, direct imagery, astrometry, just looking the motion of the star due to the planet, and so on. So I will have no time to discuss all these other possibilities. So if you look at a diagram where you have here the mass, so the Earth's mass will be here, and then it is logarithmic scale, so here is 300 times more than the mass is Jupiter, and here is a period, also a logarithmic scale, 10 days, 1 year, and so on. So the Earth is 1 and 1, so will be here. Here, and Jupiter will be someplace here, and so on. But you see that the colors corresponding to the different detection techniques, radial velocity technique, transit, and so on, are located in different places. The transit technique, the most interesting for you, are mostly adapted to detect relatively short period planets. The velocities is mostly longer planet, and for the very long one, you have to do image on things like this for today. So this is, but you see also the dynamics is huge with, I don't know, maybe a factor 1,000 here between the mass of the smallest one and here. So radial velocity technique, how it works. Here you have a cartoon where you have a star here and you have a planet orbiting around. Remember, you cannot see the planet itself, but if you are measuring precisely the velocity of the star, by the Doppler effect, you will have the possibility to detect a very, very small change of the frequency emitted by the star itself. And when you interpret this small change, you have the possibility to say, oh, the velocity of the star is changing. Sometimes the star is moving in your direction, sometimes the star is receding. So something is turning around, and after a few calculations, you can derive the mass, the period, and so on of the planet. This was the method used 20 years ago to detect the first planet orbiting a normal star. And maybe something like 1,000 additional planets was discovered by this technique. So what is a spectrograph? A spectrograph is an instrument located close to the telescope and trying to analyze the frequency emitted by the star. And you see it's a relatively complex instrument in the vacuum because we are measuring extremely small change of the velocity. It's typically 1 part is 1 billion. It's a small change of the velocity, and this is the reason why it was the discoveries done by this technique was relatively late, only 20 years ago. This is an instrument we have developed to be installed at La Silla Observatory in Chile. So just one example of the discoveries. This object, it's a very complex system. It's a star, not a relatively bright one, with 7 planets detected orbiting. So here you have the velocity, here is the time. You see that you have more than 2,000 days here, and every red dot corresponds to one measurement done in one night. And after 2,000 days, so several years, you see that you have a cloud of red points here. It's not very easy. Maybe we can suspect that you have something like this. But when you let the computer to analyze this data, it says that this is a result of 7 planets. And you see this planet, one is only with a period of 1 day, 5 days, 16 days, and so on. And the mass are very small. 1.5 times the mass of the Earth, for example. And so you see the few of these objects are extremely tight, close to the star itself, and evidently we do not have anything similar in the solar system. This is the first example of the huge diversity of planetary systems you can find in the universe. So you see that you have the velocity curve, so the velocity, the time, and you see the change of the velocity. And when you superimpose all these curves, in fact, you have this object here. So I will not discuss more this kind of techniques because it's not the core of what you will have to do. And we move right now to the most important aspect of the technique of transit. In 1999, we have discovered a planet orbiting a star with a period of 3.5 days. So 3.5 days, this was also one of the most important facts discovered during the last 20 years. You can have very tight system. We have sometimes big planet orbiting very close to the star. So if you have a planet so close, a planet like Jupiter, so close to the star, you have a relatively good chance to have an eclipse. In fact, we are using more transit to describe this fact. So what it is, if you have a small astronomer looking here, the planet will cross the disk here, and you will see a small drop of the luminosity just at the time when the planet crosses the disk. So we cannot see the planet crossing the disk. You only have access to a small diminishing of the luminosity. It is what you will see in the game. So the Doppler spectroscopy gives access to the mass of the planet, This technique gives you the radius of the planet, because it's absolutely evident. If you are taking 1/100th of the luminosity of the star when the planet crosses the disk, in fact, you can compare the disk of the star to the disk of the planet, and you have access to the size of the planet. And so with these two quantities, you have access to the density, and after you can say maybe it's a gaseous planet or a rocky planet or icy planet and so on. So this is really the start of a new discipline, is comparative planetology. So this, for example, you see the real, okay, this is in our solar system. So in the solar system, you can see really the transit. So this is Mercury transiting the disk of the sun, November 2006, and you see the size of the planet is very small compared to the disk of the star. So evidently the contrast of the eclipse, of the transit, is extremely small, evidently it's very difficult, and it's a good reason maybe to go into space to continue this kind of measurements. So what it is. So this is a cartoon. You have the star, you have the planet orbiting like this, and sometimes you take part of the luminosity of the star, so you have the drop of the luminosity, but at some moment later, the planet will be itself behind the disk of the star, and in the infrared, you have a small decrease of the luminosity, and this is directly a measurement of the temperature of the planet. It's very fascinating. You do not see the planet themselves, but you can have the mass, the diameter, the density, the temperature of the atmosphere, and so on. So you see, this is a very, very rich technique. And also you have a phenomena of phase, like you have for the moon here. So if you have the privilege to have access to a telescope working in the infrared, in fact, what you observe, this is a transit when the planet is in front of the star. Here, when in the infrared at 8 micron, when the planet is behind, this is here. But due to this phase effect, in fact, this is a small modulation here, so you can have access to a lot of complexity of the exchange of temperature, of energy in the atmosphere of the planet. Just to give a first example of the richness of this kind of technique. So this is a good example, very simple. Here, what is the idea of the transit? It's very easy in principle. You measure with a tool, a telescope, a satellite, and so on. You measure the luminosity, for example, of 1 million stars. Every 10 minutes, you take a measurement, during several years, and after you analyze. And what you observe, that the luminosity of the star here versus time, here it's only 1 month. You see the noise of the measurements. You see it's only 5,000. It's very small. 1% it will be something like this. So and at some moment you have a drop of the luminosity because you have the transit of a planet in front. If you analyze carefully this drop, you see the shape here of the planet when it transits here. And this could be done from the ground. You have a lot of experiments giving a lot of results, but evidently from the ground you have access to relatively large planets. It's very difficult to have access to the smallest. And here you see, I will not describe all the details, but one very fascinating possibility will be that here is a planet in front of a solar-type star, and you see that the atmosphere of the planet is filtering the luminosity, the light emitted by the star. So if you compare the spectrum when this planet is in front or when the planet is behind, you subtract the two and you have access to the chemistry in the atmosphere of the planet. Absolutely fascinating. You cannot see the planet themselves, but you can start to analyze the chemistry of the planet. This is a small history of what happened in the domain of transit during the last 20 years. Here, this is a solar system. You see this is the radius. The Earth is here. Jupiter is here. It's 10 times larger, something like this. You have a factor 10 about here. Here you have the mass. You have the Earth, Venus. Neptune is the icy planet. Saturn, Jupiter is a gaseous giant planet. You see, this is the relation between the radius and the mass. And then after starts the domain of the discoveries of exoplanets. And we discovered in 1999 this object here with 3.5 days of period. We have a collaboration with US colleague at Boulder Observatory, and one of these colleagues, for fun, built a small telescope, 10 centimeters, in his garage, paying by himself. And he measured the planet, the star we have indicated, and exactly at the time we have predicted from the velocities, or the change of the velocity of the star, you see this small drop at a good time. Here, it was September. The period is 3.5 days. Why it is 7 days here? Because if you have the transit in the middle of the night here, the next one will be in the middle of the day, so you cannot do it, measure it, and then 7 days after you have again the transit. Okay, this is the first relation between radius and mass for exoplanet. And then after, 5 years later, few other objects appear. All these objects here are in the core of the galaxy. You have this region where I showed before, where so many stars. So some Polish colleagues did some measurements, and we observed a few transiting planets here. And also from the ground, we have discovered this one, or a US colleague have discovered this one, and so on. So we start to populate this diagram. Wow. Yes. And then after arrive new objects detected by different kind of techniques, different team in the and you start to have object with lower mass planet here, 2007. Yes, 2009, you have quite a lot. And this is the time where starts the operation of the satellite, the space mission Kourou. And for the first time, an object, Kourou 7, was discovered with almost the mass, a little bit more than the mass of the Earth, and a larger radius, larger mass and larger radius. So we are moving in direction of rocky planets. And you can notice a lot of strange things here. Why? We have all the measurements of gaseous giant planet larger, with a larger size compared to Jupiter. Why? Why you have a sphere of gas, hydrogen, and helium? Why it's possible to have a larger? It's a huge change, because you see you have a change of maybe factor 50% here, so it's a much smaller density. What is the physical reason why you have some kind of expanded Jupiter? It's still not solved today. And then after 2011 arrived this fantastic mission, the Kepler mission. And you see you have few observers coming from different other techniques, but you see the huge galore of observation, again with always this characteristic of inflated gaseous giant planet, and a lot of objects starting to be close to the Earth. 2007, here you see, we still have, I don't know how many today, how many planets with both the candidates detected by Kepler, it's a lot, it's several thousand, but we do not have every time the mass of them, and we are working presently to try to get also the mass of this object detected by Kepler. So this is a historical view of what is going on. No. You do not want to move? Okay, yes. I know we are closer to the game. So what you will have access in the frame of EVE Online, it will be something like this. You see that you have a lot of measurements of the luminosity of stars. In the first step, you will have something access to more than 100,000 images like this. You see, it's a very small change. This is a very, very teeny part of the luminosity. So this is the noise of the measurements. And then after you will have access to some tools to see if something interesting is embedded here. And you will see in this case that you have a transit of a period of 5 days and here. So this will be what you have to do is to try to see if we can detect some new object like this. So I can repeat here that you will have access to different parameters. Here, the semi-major axis, the radius, and so on. The contrast of the depth, this gives access to the size of the planet, and so on. So, evidently, the computers are extremely efficient to find if you have a periodic signal in this luminosity curve. The computer will be extremely efficient to find a periodic signal. But sometimes, the things are not so easy. For example, here, you have a signal that is not periodic. If you try to compare at a certain period the drop of the different transit, you have something like this. So see, sometimes they are in advance, sometimes they are delayed, and so on. So the period is not perfect. So what is the reason of that? In fact, in such a case, is the problem of the interaction between several planets. If you have several planets orbiting the same stars, sometimes the gravitational influence of one planet to another one will delay the transit or increase the velocity of the star and have a change of the time of the transit. This is one typical, and the tool, the computer will have some, if the delay is large, the computer can have some problem. Here you have another different case, where sometimes the star is magnetically active. So you have a lot of spots, magnetic activity, superimposed to what you are looking for is the problem of transit. And you see, for example, in this case, the main curve here is due to the change of the luminosity of the star, but in addition, you have transit of a planet. So suddenly, if you are using a computer automatic tool, maybe it will be mostly impressed or sensitive to the most important characteristic. But if you are looking by eye, you will have a chance to see the transit of the planet. You have also a very, very interesting case. It's what is called the circumbinary planet. Most of the stars, I would say 2/3 of the stars, are in double stars, binary stars. the sun is a relatively exceptional situation because to be alone. But most of the solar type stars are locked in double stars like this. Let's imagine you have a situation like this with two stars, and in addition you have a planet orbiting outside the orbit of the two stars. So you will have the possibility to have transit first of one star and then after to the other one. But then when the stars are changing of position, the timing of the transit will be affected. And it's the reason why here you see you have this is not a transit, a planetary transit. This is star B, eclipse star A. Here star A occult star B. And this is the transit of a planet in front of star A. And then this is the transit of another planet transiting a star B, a smaller star, you see here. So you start to have a relatively more complex pattern of transit. Very interesting case. And maybe, in some sense, maybe one of the most interesting case is the fact when you have one single transit here. You have the variability of the star. You know that the sun is also affected by magnetic activity. So you have change of the luminosity of the star, but suddenly you have something much shorter. And this is a transit. But sometimes the span of the mission, the space mission, is too short to have a second one. So this corresponds to a relatively long period object. And in some cases, these are the most interesting case because the distance between the planet and the star is such that this planet could be maybe in the habitable zone of the star. So very interesting case. So the material you will receive or you will access is coming from, in the first step, it will be coming from the Kourou space mission. So it's something like 106, okay, a lot of stars measured. And so you have quite a lot of luminosity curve. And part of this material, you have a lot of eclipsing binaries. Eclipsing binaries is two stars orbiting each other. And so sometimes one star is in front of the other and so on. So this is very interesting, but this is not planet. You have something like 500 candidates of planets. You have 36 identified planets, including the rocky planet Kourou 7b. And you can do some extrapolation of what we have, and we can anticipate that we still have a certain amount of planets still not detected. In a further step of this video game, you will have access to the data coming from the Kepler satellite. It's also a huge amount of data. And in 2 or 3 years, you will have access to a new mission called TESS mission. It's a small NASA satellite, but with a very interesting characteristic to analyze only the brightest star around us, so the closest planet with this kind of transit. So a huge quantity of material, some fresh, will be available in the future. And here, okay, this is a global view of the Kepler mission. Here, this is the radius of the planet detected by Kepler, and here the period. And you see the satellite was measuring during several years. The first season, it was only able to detect the blue dots. Then after a second year, it was able to measure longer period. The third season was the yellow dots, and unhappily, the gyroscope died. So it was not able to detect longer objects here. And so the reason we are still missing that region here. Maybe we have single transit, but we don't have periodic transit here. And so the one Earth radius, one period is 300 days, the habitable zone will be here, and happily we do not have object here. We have some small mass object here, but not solar type stars. And here this is one typical system with several 6 transits. Here you can see detected by 6 transits orbiting the same star. Kepler 11 detected already several years ago. So the story is continuing. On the ground, you will have 39-meter telescope presently in construction in Chile. You have a new spectrograph able to measure extremely small planet at Paranal Observatory north of Chile. One experiment on the ground, and also working in the infrared in Hawaii and so on, and satellites, Cheops, small satellite to be launched in 1 or 2 years, to do precise measurement of some transit. TESS, I already mentioned, and this you will have access to this kind of data. The James Webb Telescope to be launched in 1 or 2 years, and so on. So Plato, it's a very interesting mission to be sent in the space in 2024 with a special goal to detect small planet transiting star around bright stars, because they are the most interesting, because they are close of us. So you have a huge activity in the domain of astronomy on this topic. Here, NGTS, this is a mission with small telescopes in the desert of Atacama, and with this is the present planetary radius versus radius of the star, and we can expect to explore this domain here. TESS, I already mentioned, launched very close in a couple of months. Cheops, I already mentioned, to provide precise photometric curve of some transit. Plato in 2024, with the capability to detect a lot, to do maybe 1 million of light curves, try to detect maybe 100 or 1,000 super-Earths in the habitable zone, so planet with few times the mass of the Earth, and so on and so on. Maybe moons, ring, exocomets, and so on. So it's a fantastic mission expected from ESA already. The design is active, and with a huge set of small telescopes able to measure different places of the sky. So this is again Kepler. So again, the radius, the period of the detected transit, and you see you have some code of colors. So when you have one single planet, is the black dots. When you have 3 planets, is the blue dots. When you have 5 planets, is okay, this color, I don't know the name. And when you have 6, it's red. So already you see that this technique, the transit, provides a lot of multi-planetary system. And again, Kepler, here the same plot. We have the radius here. The Earth will be on this line. Jupiter will be something placed here. And here, this is not the period here. It's the temperature in the atmosphere of the planet, because if the planet is very close, it will be hot. If it's very far, it will be cold. But you see, this habitable zone is here. This is the region where you have the chance that the complex chemistry of the Earth, on the atmosphere, will be able to provide the condition for life development. So, you see, and a zoom of this region here. This is the habitable zone. This is the radius. And you see, in fact, you don't have so many interesting points for the moment. Here is still an open question. In La Palma, we have a second instrument like I showed before, where we are measuring carefully the mass of planet with small transit. When you have a small transit, it corresponds to a small planet, a rocky planet. So if you have the radius in unit of the Earth, and you have the mass here, and you see that we have every object we have measured with special names here, you have certain relation between radius and mass, and suddenly when you are at 5 or 6 times the mass of the Earth, suddenly you have a much larger planet. So these are rocky planets. You have the same, these different curves correspond to different composition. You have Venus and Earth. So if you have the same composition of Earth and Venus, rocky planet, you have this object here, and suddenly you have a big envelope, you have different kind of planet. So probably the habitable planet will be confined to this kind of object here. And just to finish with few nice location for astronomers, and this is Paranal Observatory, north of Chile, Atacama Desert, something like 240 to a little bit more than 2,000 meters of altitude, 8-meter telescope, 4 8-meter telescope, plus a certain amount of smaller one. And as I showed before, if you compare the spectrum when the planet is in front of the star or when the planet is behind the star, you have access, a very teeny difference between the two. So you need very big telescope to have enough photons, but when you are analyzing the difference of these two spectra, you have access to this kind of curves. So these are all the red and the blue curves and so on correspond to different composition of the atmosphere, and unhappily the observations are not so precise. So you have access by this kind of experiment, you have access to the composition of the atmosphere. Here, this is the project of the 39-meter telescope in construction in the Atacama Desert. Just have a look on the big track here, or the car here. It's huge. Let's imagine the mirror of this telescope will be larger than the room here. Okay, Paranal is here, the present observatory, and the 39-meter telescope will be on this mountain here, Chermo Armazanes, a little bit higher in altitude than this one. And we do not have to forget that in a couple of years from now, we will have the launch of the James Webb Space Telescope, the successor of the Hubble Space Telescope, with a mirror of 6.5 meters in the space. And evidently, this instrument will also compete to do nice measurements in the frame of extrasolar planet. So I will finish my short lecture on exoplanet with one fascinating object. So probably you have heard about 1 month ago. It's called TRAPPIST-1. It's the name of a small telescope having first identified this object and published in Nature 22 of February. So what it is? So I hope you recognize this kind of drawing here. You have the luminosity here. Okay, this is very small, 1/1000th of the luminosity. And you have characteristic of transit. And you see sometimes it's very strange. They are not periodic. You see that you have transit almost any kind of position. And this is a continuation here. And if you analyze carefully this data, you see sometimes the transit time is shorter here compared to here or to here and so on. When you analyze the different colors or the different duration of transit, you have these objects. And you see that you have one planet with a period of 1.5 days, 2.4, 4 days, 6 days, 9 days, 12 days, 14 days. Incredible. 7 planets extremely packed here. And these planets are orbiting a very small star, with a very small luminosity. So if the luminosity is very small, what is the consequence? So you can go closer to the star before it will be too hot. So the habitable zone is relatively close to the star. So here you have the same plot here. You have the position of these 7 planets, and the habitable zone is the gray zone here. So you see that few of these planets are in the domain of temperature where the chemistry of life could appear. And this object is only at 39 light years, relatively close, and this will be a fantastic object for follow-up measurements. So this is a different interesting drawing. So we are not using the distance to the star here, but the flux received by the planet. And here you have the solar system, Mercury, Venus, the Earth with the moon, Mars, the asteroid belt, and so on. And the flux received by the Earth is, we use the definition, is 1. And these are the TRAPPIST planets. And you see you have several of these objects receiving the same quantity of energy as we are receiving on the Earth today. So we can dream maybe you have a civilization here, and maybe another one here. Evidently, if you have 7 planets orbiting each other so close to the star, so evidently they will interact together. And the net result is that the timing will not be like a Swiss watch. It will be, sometimes the transit will be a little bit in advance or delayed. And for example, you have few minutes. This is sometimes it's in advance by something 20 minutes, delayed by 20 minutes, and so on. And then the all curve correspond to a different planet. So this permits the determination of the mass without access to a spectrograph. So this is very interesting. And do we have the possibility to detect life? Okay, except if you have access to a beautiful spacecraft like you have in the EVE online game, you are obliged to analyze the luminosity of the star and try to detect what is called biomarker, so signature of life development. You have different possibilities. Some are extremely complicated, but what will be the first one you can have a dream to use is try to detect if you have some vegetation. So if you have some molecules able to convert the energy from a photon to some chemical, to store energy in the molecules. In fact, evidently the most well-known is chlorophyll. And you see this curve, the green curve corresponds to chlorophyll. This is a reflectance. It's in the blue, you have the vegetation reflect very, very low quantity. And suddenly, it reflects a lot, 80% of the luminosity. So you have a discontinuity of the reflectance of the vegetation due to the chemistry of chlorophyll. And this is true for other kind of molecules. So every time you try to pick some energy to the photon to transfer to the chemistry, you have this kind of situation. a polarization here of the luminosity and a drop or increase of the reflectance. So if you have the capability to see the change of the color of the star of the planet, you will have maybe the ability to detect continents with vegetation. And this is just at the edge of what we can do today. So this maybe could be the first step to the search of life. And I have to thank you.